Thank you. Thank you.
So this is yours.
Yes.
I'll start.
Okay, thank you. Can everyone hear me okay? And got the password on the first try. Probably means I need to improve it there. Okay, let's go. Let's go from the start here and get my clicker. So yeah, I'm Shane. Hello everyone. I'm delighted to be here. Delighted to be in Oslo. Never been in Oslo before. Wow, it's just, I mean, somewhat the city, the atmosphere. It's fantastic. I feel at home. So much at home that people continue to assume I can speak Norwegian. So that's a new kind of continuous learning goal, is to get some basic conversational Norwegian, but with hopefully not a horrible accent. So, willkommen, is that close-ish? Yeah. All right.
Sounds German.
Okay, sorry. Um, so some things about myself. I do work for Cisco, as Lena mentioned. I also worked for IBM for many years, and before that, smaller IT training company called Global Knowledge. I've had a lot of opportunity to do a lot of consulting, working with various companies, and I've kind of toggled back and forth between privacy security domains and then more general, shall we say, analytic domains, data science domains, whatever your taxonomy is for, enhanced statistical analysis with programming and as well. There's a phrase I'm kind of fond of that, a data scientist is a statistician who can program decently, or a programmer who knows a little bit about statistics. And there's a bit of truth to that. So I've gone between different domains, as I say. Sometimes as well, I've had some cross-training opportunities, been fortunate to work in weather. So the weather company was an acquisition of one of my previous companies. So it's interesting how wildfire management and weather has some correlation in the security domain, for example. And also in healthcare, which is both a sort of good cross-training and also an area of obvious concern, right, for all of us in terms of privacy and security. And currently I work now at Cisco within our security and trust organization. I'm thrilled to be there. I work with Dave Schwartzberg here. We're on the front lines in operational security, as well as others. Shout out to Chris Benson, another first member, and he also he typically organizes, yeah, sets up monitoring infrastructure, etc. But I'm here today really to talk about my own independent research, nothing internal to Cisco or anything like that. And I want to talk about something that's very near and dear to me. So I know I think we have at least one more presentation in this domain, and I'm grateful for that, because the story I'm going to tell today is probably a bit different. This is going to be less about how machine learning and how data analytics can help us in our struggles, and more about the flaws and the holes that can be exploited, the weaknesses in the algorithms. And let me be clear about this too. I do think, and I do strive to use these tools for good, both for myself and within my work. But they're kind of like family to me because I've been working with them so long. And I think we all know we're as hard on our family as we are on anyone else. So I'm just being really hard on my family, I guess. So please don't take it as I'm telling you that all this stuff is just scary and flawed and all of that. Like any technology, right? There's going to be vulnerabilities, there's going to be exploits, and ultimately there's going to be incidents. And we're just trying to stay ahead of the knee of the curve in terms of dealing with this. Okay, so let's roll through the agenda a little bit, just so you know where I'm going. And there's a point. It's not just pure abstract data art, I suppose. So we're going to start with an overview of analytic attacks. So machine learning is just a more sophisticated version of analytic attacks. And sometimes I think there's a little bit of misconception. People assume when there's discussions of exploits involving statistics that it's always machine learning algorithm. That's not the case. Okay, it could be something very simple. It could be something like some of these right or left-wing groups, finding ways to DOS news stations, because they have feedback tools, right? They take in people's feedback and things like that. People mess with GPS, if they're or reporting locations and so forth, like that there might not necessarily be a statistical learning algorithm involved there. So we're going to kind of just cover that landscape, and then we'll delve into privacy attacks and differential privacy. I think that kind of sets the stage moving forward. We're going to talk, don't worry if anyone's worrying, is this just a privacy discussion? No, it's intended to be both, privacy and security, safety, shall we say, if we want to taxonomize that way. It's interesting, all the things, and we have to come up with names for things. It's a constant struggle. But anyway, it provides a baseline, I think, for understanding that helps build knowledge. A lot of these concepts, you have to, at least for me personally, you have to play with the idea a little. It's not going to just, eureka, I understand it, I get it all. I don't get it all. Nobody, anyone who says they get it all, I question that a bit. Certainly those that know more than others, but it's usually just like within other domains of security and privacy. It's very specialized, right? CSERTs tend to be really, really good at what they do. Vulnerability management tends to be really good at what they do, and so on and so forth. So then we'll move into some machine learning attacks. We'll kind of get an overview of the landscape. We'll look at membership inference attacks, which is a specific type of privacy attack that's of tremendous concern, and also has some generalized principles which apply to other methods. And then we'll get into some security attacks, poisoning, adversarial inputs, and then finally we'll wrap up with just some exploration of CVSS. I know there are probably folks in this room that are much, much more deep in terms of their expertise with respect to CVSS, but as it's a first TC, I thought that it might be interesting to go through a few exercises there. And then finally, I'm going to give credit where credit is due. Let me be clear, a lot of what I'm doing is typical red teaming, right? Looking for exploit code POCs and sharing that. And I'll be sure to provide references so that you all can continue to do research, and of course, just to provide my colleagues and those that are helping the overall community with some credit. And then we'll wrap up, and hopefully, I'm sure we'll have some time for questions. Okay, so the analytic attack overview, I think this is the best way to distill the landscape here in terms of what's happening. So black box, white box, gray box, I think these are familiar terms in the security space. The gray box phenomenon within machine learning is very interesting. You will see, hopefully, as we go through some of the demonstrations and some of the discussions here, that attacks that are currently now black box, in other words, the parameters of the model have somehow been discovered, can segue into gray box and ultimately potentially into white box. And we'll go through how that happens. Also, it's good to kind of bucket security and privacy and then look at the overlap and also look at the tension. There is quite a bit of tension. Some of the methods that work in security actually are, they're detrimental to privacy, which is one of the things in this active research in this area, which makes it really difficult. And then ultimately as well, I think it helps to from a high level, particularly if you want to take this away, you don't necessarily want to get into the weeds, but you want to know, what do I need to worry about if I'm managing an organization or I'm managing people who manage an organization? You're looking at deception scenarios and theft scenarios. And not always, but typically it's some kind of bypass on the deception And then for the theft, it's exfiltration, right? Exfiltration of people's private information. Sometimes exfiltration of the model itself. So, and that's model inversion is the term you'll hear many times when people are discussing that. All right, so let's talk about the attack surface a little bit. And this is really, I'm going to take some time just to kind of go through some of these. Prediction contests is really where I started, the alarm bell started going off for me many years ago. So I don't know if you've heard of Kaggle. It's a machine learning competition. There's sometimes cash rewards or incentives. There's also tremendous incentive, for example, if you're on a data science team working for a company and you win one of these competitions. There's also direct prediction contests that pay out in Bitcoin for predicting stock market, different securities, et cetera, predicting anything. As a matter of fact, there's sites that pay out in Bitcoin for predicting the price of Bitcoin. Is that meta enough? I mean, what times we live in. Anyway, the point is, this is a breeding ground. And the temptation is there. You will see if you enter one of these contests yourself, the temptation will be there to not build the most general machine learning algorithm that solves the problem, but to learn what the leaderboard is. Because there'll be a leaderboard upon which you're judged, which is supposed to be a private data set. But obviously, there are lots of ways to poke and prod at that leaderboard, depending on what rate limiting they've done, and maybe they make you sign up for a new email, right? So then, oh, it's so hard to get multiple emails these days, right? So this is kind of like the training ground. Machine learning as a service is obvious. That's probably where the most, and I'm going to try to refrain from referring to specific companies in terms of incidents and things that have happened. But let's just say that if you look at machine learning as a service offerings right now, you'll notice that many of them are saying things like, this one is currently deprecated, we have a new one today. So, and anyone, I don't know if we have anyone here who's in a vulnerability management team or is involved in that space, so that's sort of like a patching regime. I'm not asserting that that is completely to do with security and privacy issues, but let's just say reasonable probability that, that's the case. And obviously, that would be where your your black box attacks would be. So you would be querying these predictive services, seeing how the model acts, and continue from there. Crowdsource apps as well. That's where feedback weaponization comes into play. So anywhere where users are supplying input, which ultimately will feed a model. And then finally, there's research academia, sites and repos. So all of this great open source knowledge, open science, well, unfortunately, once again, we have the double-edged sword. That is where a lot of exploit code is being derived from, and that is where playbooks are being written, with the mathematical proofs and the code of how to do this. If this was framed in a different domain, I think there would be people kind of just screaming from the rafters about it, right? But because it's within a community that is honestly, I have to give credit. That's very forward-looking. They're very very passionate about privacy, security, etc. And they don't. It's not there. In the past, there hasn't been a lot of assumption that this, the malicious use is there. And I've been one of the folks sounding the alarm, and I'm hoping that you all will help spread the message as we move forward. And then, of course, any simple app that's using data for analytics is going to be useful. So let's go in. Like as I said, we're going to start with privacy. Don't get too caught up in whether it's privacy or security. I'm just trying to help provide some structure around what I'm talking about. So this is your basic privacy attacks, and there's a whole list with very fancy names of these different types of attacks: record linkage attacks, difference attacks, etc. But essentially, this is the loop, right? What can I learn from functions permitted on the data, and what external data sources can I combine with the data? And you've got the whole interwebs, right, at your disposal when you're doing this. So it's not as if, sometimes I think, and initially for me anyway, I thought, well, okay, there's not that much data out there, but then if you really think about it, and if you're a clever person, you know, and you've spent time learning learning security technology, learning systems technology, and then learning statistics, yeah, there's a lot there. So that brings us to differential privacy, and here's where I have to give my first sort of kudos to Ms. Dwork. Cynthia Dwork is kind of the founding mother of differential privacy. And I won't read this all to you, but I think it's worth having it up there. A few things I will point out. Adversely or otherwise. So what that means as well is, even if the intention was not malicious, right? It's still not okay, right? Like, you know, to expose data. And when we're talking about exposing data here, we're not talking about directly, here is the record, here's the database, take a look at it. Like, this is derived from statistical calculations or derived from continually manipulating a model's predictions until you figure out what's going on. So, yeah, pointing out adversely or otherwise, and then, of course, no matter what other studies, data sets, or information from other sources is available. One more note on Cynthia now, a lot of her research is in fairness and fairness algorithms, which is a really interesting space to look at. Not gonna say too much about that there, but I just, if you're curious, I know we've got lots of smart, intellectually curious people here. I think that you might be interested in just Google Cynthia Dwork, fairness, and you'll get there. So differential privacy in theory is that masking the data only gets you so far. You need to consider privacy in the data-driven functions themselves. So sort of moving towards that concept of privacy by design, which is actually written into GDPR somewhere, I believe. And then anticipate external data sources. In practice, can you guys want to yell it, or I don't know. You make noise, lots and lots of noise. And noise, of course, meaning randomness. It's funny, a lot of this boils down to a noise war. And you'll see that the attackers also use noise. And interestingly, the defense, in many cases, is noise, is the randomness and the chaos in physics and the natural world around us. So how does it kind of work? We can walk through that. So you evaluate the privacy of a function, add some controlled noise, and I'll try to show you how that works, but essentially it's noise that you're aware of, that you've provided yourself, and that can be kind of reversed mathematically. Not all of it, because that would kind of defeat the purpose, but you reverse some of it mathematically so that you get a reasonably accurate statistic while maintaining privacy. So you calculate statistics and account for that noise, you evaluate the accuracy, and you may remove some noise, and that's kind of the circle and the way it goes. And what you end up with is a balancing act here. I'm showing sort of an aspirational scale here. Like, it's typically more this way, right? As a matter of fact, right now, there's a lot of discussion about how differential privacy is getting more and more difficult because of the amount of noise, given the sophisticated level of the algorithms. But let's talk a little bit on the right-hand side, too, about obviously you want utility, and that includes accuracy. Urgency is something else that I would throw up for consideration. And this all has to be, you know, this model, this sort of trust model needs to be built, I think, based on your organization, based on your circles of trust. But urgency, an example would be, you know, is this a life or death type of situation? You know, then maybe, you know, you're willing to sacrifice a little bit of sensitivity for that particular scenario. Or maybe not. As I said, I leave this to the audience. This is not easy. This is not easy. A note on sensitivity as well. This refers to the sensitivity of the data, but also the sensitivity of the functions. So not all functions are created equal. For example, a sum is a much more sensitive function than a mean. A sum is really just a tally of everything, right? So once you know one record and you subtract one, you're triangulating fairly quickly. So this brings us to our first little demonstration. I'm going to be using Jupyter notebooks, which will have some code in there and a little bit of math. Please don't obsess over the code. I learn by experimentation, and that's how I like to convey knowledge as well. So focus on the outputs, and again, try to get your mind comfortable with what's going on here, because it's all very thematic. It starts at first. It may seem like hieroglyphics, but it starts to kind of click. And I'm actually going, since we had lunch, and probably some people are full, and maybe not. This isn't just exactly what they want to talk about. So I'm going to have a few volunteers. Dave is voluntold. And as you can see up here, provide a fake name. I've already put some fake names up there. Jane Doe, Anonymouse, Why Ya Askin', and as my wife likes to say, she's from the southeastern United States, none ya beeswax. So these are the names. We're going to be privacy conscious, so you don't need to volunteer a name. I just ask that you take a coin that we can use for later. So I don't know if anyone else is comfortable flipping a coin for me a couple of times. There we go. There we go. And I thought I saw one more person back here. 3's good. I can flip for the last one. All right, here we go. And I didn't seed this or anything like that, so this is all going to be live code. So a little bit of risk there, but I think it creates the experience. It makes it a little more tangible. So what I've done here is I've actually created some answers. And actually, let me go through. So the first gentleman I gave the coin to, I have a question for you. Do you like rugby, yes or no? Yes or no? No. And do you like rugby, sir?
I don't know.
Binary. It's a binary question now. No, okay. I'm seeing a pattern here. And one more? Yes, okay, good. And I myself do like rugby. So, all right. Now we have our nice data there. So what I'm going to do here is just do what we just did in an automated way. Create some fake data, because I don't think you'll be too impressed with me attacking 4 records, quite honestly. And we'll take a look at it. So we've got our responses here. This is just the head of the data set, the first 5 rows. And then here I'm just looking and pulling out those names just to see your names are in this data set as well as a couple of thousand more. So I don't know if you all can see. Can someone tell me it's fairly obvious what the pattern might be in this record? Like what about this particular database may be problematic if you were, say, a reasonably savvy data professional? Yeah, well, did someone say alphabetized, I think? So, yeah. Yeah, so the names are in alphabetical order, both by first and last. So that's very useful, obviously. And I'm starting with, and for the most part, I'm staying in the kind of toy playground of, this is blatantly obvious what's going on for the intuitions, but obviously attacks can get much more sophisticated than this. So this is kind of the building blocks of what's called a difference attack. If we calculate some statistics, in this case, the mean, the percentage of people that are actually, responding, we get a 0.72%. And then if we look at the percentage that are yes, again, in a certain range, from record 1 to 202, we see that the number went down. So that number going down means that we've gotten some information now. So we know we can start to narrow down, okay, someone in here does not like rugby, right? Got lower. And this is kind of how it works. And if anyone has any experience pen testing, it's never going to be exact, it's never going to be perfect, but once the vultures can start circling, then away we go, right? Also, there's other data sources to consider. So many times what you will see in studies and academia research sites, sometimes, hopefully not, but occasionally on a government site, they'll say, our study was conducted as follows. We polled 2,000 participants from the following regions of the, so right there we go. We've got basically the anatomy of a difference attack. So I've got a little function here to run through, and I don't expect this to be overwhelmingly impressive, but just to show you that simply by looking at the difference between the data with all the data and then the data minus a certain record, you can actually derive some of their private information. So differential privacy. Let's go ahead and take that for a spin. So these are the audience volunteer instructions. What's going to happen, it's a little confusing. There's 2 flips sometimes, but essentially, if you're going to flip the coin, if the coin comes up heads, we're going to provide we're going to stick with the truth that you provided, and if not, we're going to flip again. And if it's heads, it's going to be a 1. If it's tails, it's going to be a 0. This comes from a very, very old algorithm in sociological studies, which I'll be referencing later if you want to read it up, called randomized response. And I don't know if anyone's ever heard of plausible deniability, so that's where this comes from. And believe it or not, while I'm showing you a very simple toy example of this, this is the root of differential privacy. So let's go. So here's our data once again. And let's start flipping. So what do you got, a heads or tails?
Tails.
Okay, I believe you.
The 1.
And a 1. Okay, so we'll change that to a 1. And then, Rhoda? Oh, and we're going to have lots of noise.
Heads.
Heads, so we'll stick with the truth for you. And then one more from the gentleman in the back. Heads, and you're, you get Rhoda's in here. So you were heads as well. Yep, so we'll leave you the truth. So I will flip now. Hopefully this is a fair coin. It's a euro, so it has to be, right? Unfair. That was tails. So I got to flip again, and I got a heads, so I'll put a 1. That's going to end up being the truth anyway for me. But hopefully... oh, you did like rugby. So this one should be 1? Okay. All right. Yeah, that was your truthful answer, and you flipped heads? Yeah. Okay. Thank you for correcting me on that. Okay, so we've created some randomized response. Once again, we're not going to do this for all the records in the data set. We're going to go ahead and automate this. And so now we've created, so it's pretty obvious we've created some noise, right? But the clever part, and the part that really for me made me think, I'm going to keep working on this stuff. This stuff is pretty cool. Is that using some simple math, you can see that not only can you create noise to mess up your data, but you can actually come up with some decent statistics. So what we're doing is essentially just averaging the truth with a 50-50 chance, assuming our coins are fair. So, and if you look and go through this, just some really harmless math here, you've got your true stat plus 0.5 for 50-50, and we'll take the average of the 2. There's 2 of them, we divide by 2, and that gives us our noisy stat. So then if we do just a little bit of algebra here, the true stat plus 0.5 equals 2 times the noisy stat, right? We're just multiplying both sides by 2. And then if we subtract the 0.5, then the true stat, roughly, tilde, approximately equals 2 times the noisy stat minus 0.5. Or, as they say in the sort of academic literature, the differential privacy stat, the differentially private stat, is equal to 2 times the noisy stat minus 0.5. So let's just make it work in the codes here. So we've created our noisy stat, And the true stat is 0.72 and the noisy stat is 0.6. So that's not very useful, right? Private, but not useful. If we go through the first step of the algorithm here, we can get to 0.707. So that's a little better. So the delta is about 2 percentage points there. You can actually do better than this as well, you know, adding more data, etc. But you can see, I think, hopefully that conveys that, you know, you're much closer, and this could be close enough for many studies. Again, if you're doing the balancing act, right? If someone wants to know, you know, what is the percentage of people that responded, you can say, well, you know, about 70%. And people that have submitted their data have plausible reliability. Again, it's not that the attacks couldn't happen. The attacks could certainly happen, but they don't know, once they've exfiltrated that data, is it the truth or is it, you know, is it the coin flip? Is it the noise? So that's differential privacy. Which brings us, hopefully, tell me if the AV is not working for me. Let's wait, come on. Yeah, there it is. And where's my clicker? There we go. So let's brings us to our overview of machine learning attacks. So what you just saw there was a basic analytic attack, and machine learning attacks are essentially stacks of basic analytic attacks built into something much more sophisticated. And I want to just provide an overview, obviously in the time we have here, and perhaps some of the folks doing other talks on machine learning will give you more of an overview of just how it all works. But for the purposes of what we're talking about here, I'd like to cover a few kind of TLDR concepts. And by the way, I do also run boot camps, etc. If you're interested in learning more, you certainly can also just learn from others that I'll reference for Udacity, etc. But happy to do that. I love to do that. So let's just talk about types a little bit. So one of you can kind of bucket machine learning roughly into supervised algorithms, unsupervised, and reinforcement algorithms. So your supervised algorithms have labeled data sets. So this would be your classification problems. I have that red there because a lot of the POCs revolve around classification attacks. So that's why I've highlighted that in red. And the classification would be, you know, this is a pelican, or this is a flamingo. I don't know, it looks a bit like a flamingo to me, but I've been told it's a pelican, so, okay. Pelican it is. Pelicans are kind of terrifying animals, by the way. I don't know if anyone's ever encountered them, but regression would be more, instead of classification, just direct prediction. You know, what's the temperature, etc. How many vulnerabilities did we predict we're going to get over a given quarter? How many? And then finally, there's some other things. This is newer stuff like ranking, putting things in order, transformation, like turning it into something else, translating language. Perhaps I need something like that to get my English into Norwegian. So that's kind of supervised. And then there's unsupervised learning, which doesn't have labeled data. It just learns from data itself, which sounds amazing. Like, why don't we just use that? Why do we want to label data? Unfortunately, it's more difficult. Obviously, you know, how are you evaluating? What are the metrics, etc. But these data sets are unleveraged. And one area that is, for this discussion, I'd like to just highlight is anomaly detection. It's in green because it's actually one of our mitigations, one of our defenses. Anomaly detection could be anything from taking a standard model, a supervised model, and just looking at when it makes huge errors. But what it boils down to is what's normal behavior and what happens when something that is not normal happens. Easier said than done as well. I don't know how many of you have pristine data sets where you're like, everything here is clean as a whistle. So if there's some kind of malicious behavior, I'm going to know right off the bat. Often we have this pool of anomalies in there anyway, and they bucket that into outlier detection versus novelty detection. Novelty detection is kind of ideal, right? If you truly have those pristine data sets to work with. But we'll see how anomaly detection can help in us a little bit later. And then clustering is another algorithm, grouping things. And then more progressive, newer things on the forefront, generative models, distillation, right, compressing related to encryption, but for different purposes. How do we compress complex models and what they're putting and transfer that to perhaps a smaller model for performance purposes, et cetera. And then finally, reinforcement learning. Have it in kind of the yellow here because there's definitely discussion amongst the community that the type of attacks that are being used in classification are now being introduced in reinforcement. And that is scary because reinforcement learning is neither of those two. It's actually task performance. So this is where playing video games, creating robots that walk, doing actual work, what I call artificial work, right? Like these algorithms get rewards for doing the task appropriately and punishment for doing the task inappropriately. So it's early days, but certainly even if there's a flicker of concern here, you want to be aware of it. Okay, so some other concepts to understand, and I'll tell you why they're necessary to understand for this discussion. One is overfitting and regularization. And the best way to distill this is that machine learning algorithms are much like students that are given tests. And as we all know, we were all students or are still students. It's, give me the answers to prep for the test, and I memorize them, right? Give me new questions that I've never seen before, I don't do so well. It is stunning how these algorithms do that to the degree that you would not believe. And it is a tremendous struggle to get them to not overfit, as we say, to the data. They will fit to the noise in the data too, which is very problematic. Once again, we're back to noise. And regularization is the term used to kind of battle this. And there's lots of forms of regularization. There's something called early stopping, because many times these algorithms will iterate over the set, hundreds, thousands, maybe even hundreds of thousands of times if it's complicated data, text and images. So at some point, you add early stoppings. You say, nope, you can't learn anymore. You can also add penalty terms. And there's all kinds of methods to try to fight this overfitting phenomena. And for years, we just thought it was, well, our model really is crappy if we don't do this. So it's a best practice generally in machine learning. It turns out it's also a security and privacy issue, quite a big one. So that also brings us to model training and validation best practices. So a model gets trained and a model gets tested in general, hopefully. Hopefully you're not testing on the same data you trained on. That's like the ultimate overfit, right? You're always hiding some data from your students. And validation actually gets into schemes where you will take data and split it up. You'll throw out one example, train on the rest, test on that one, train on the rest, test on the next one, and so forth. And then parameters, gradients, and loss are related to how the model learns and how it's built. So the parameters would be what fit to the features. If you can think of data, normally there's columns and rows, or if it's more complex, it's multidimensional. There's, boxes of columns and rows and more inside of those, right? It's hard to visualize this stuff in anything beyond 3D space for us. But anyway, these parameters are fit to the data. And then gradients and loss are how the model improves. Gradients, the best way to describe them is, you're blindfolded and you're trying to walk your way down a hill. Actually, typically you're trying to go down the hill to reduce your error. If you're an attacker, you might be trying to find your way up the hill. Gradients aren't the only way, so I mentioned loss as well. For example, trees use greedy algorithms, which is a little bit different. They just look for the best solution locally, and then in the hopes that overall that will solve the problem globally. And the metrics are just be aware that that's how they're evaluated. So just like we evaluate the performance of our monitoring tools, for example, machine learning algorithms evaluate how they're doing, their progress bars. So the first attack I wanted to touch on here is membership inference, which is a nice kind of, we're moving forward from the differential privacy attacks and getting more sophisticated. So it's once again a privacy attack, and it's from a high level, fairly simple. You query the target model, you synthesize your data, you train shadow models, which we'll talk about a bit more, you train your attack model, and you learn members from the target data. So pretty reasonable flow here, but what does it mean? So data synthesis is all about taking models in a black box attack, for example, and going to this model. Let's say, pick your cloud provider of choice, has machine learning as a service, and someone has built an application. You can query that model and get the high confidence predictions. So the model the high confidence predictions is always a betrayal that that's some data that the model's been exposed to. There's other tricks that are not quite as effective, but you can throw it into the mix, which are statistics based. So you may have some experts that know something about the distribution of the population that was trained the model. And there's also just finding other data that, this kind of looks like this data, let's try it. Oh, hey, look, that's working pretty good. So from there, we get into shadow models. So we obviously can only query that target model. There's probably some rate limiting involved, right? And we obviously can only query that target model a given amount of times. So what we do from there is we go into building our own models that try, probably not in a spectacular way, right? But they try to emulate what we think the model that's been built in the cloud is doing. So you build a couple, the more the merrier typically, more shadows is better. And you take that synthesized data and you feed it to the model. And the key difference, the key thing to take away here is if the shadow has been, the shadow knows what was in its data set and what was out of it. So you can test it. You don't know that with the target model. And then from there we get into the attack itself, where we have our trained shadow, we query the target, and we can infer membership from the data set. Kind of like a more complex thing of what we were doing with the difference attack, right? So what are some things you can do to defend against this? Well, first of all, there are some best practices that you can do. Ensembling is combining multiple models into one and these models behave in different ways. If you get a sufficient diversity in your model population and you combine their predictions, it makes this much more difficult. We talked about regularization and we talked about validation. Anomaly detection can be a first stage. This kind of gets into similar to like they do for healthcare screens, right? So they don't just use one screen. So the anomaly detection can tell you if something weird is going on before it gets to your model. So you're like, hey, I don't think this is appropriate input for this model. I don't know what's going on here. And then differential privacy, as we talked about. And adversarial regularization is worth calling out. That is kind of a game theoretic application where the model itself solves a minimax problem, where it tries to maximize one model tries to trick the other essentially, and there's a regularization term that controls the trade-off there. So, you've basically created a model that's as accurate as possible while as resistant as possible to this type of adversarial attack. And then there's some benchmarking tools worth calling out, CipherCat and MBLearn. And rate limiting. Another thing just to touch on briefly, just to think about this, is we don't have to talk about it right now, but can you think about maybe how this type of approach might not just apply to that particular privacy attack, but might in general apply to other domains and other problems. So let's run through a membership inference attack. And for this data set, and I'm going to keep clicking as I talk here just in the interest of time, we're actually using a wine data set from Italy. Interestingly enough, this data set had some privacy implications because the various vineyards didn't like some of the data that was being exposed. It's since been sanitized, but just as an aside, I thought that was interesting. So here's the data set. Don't worry about it too much. This is the cultivar, this type of grape, but that's a brutish way to say it. The cultivar is more going on than that, but essentially you're the type of cultivar that goes into the wine, and it's a classification problem. So we've got basically 3 categories here. And we're going to build a target model. I'm not going to actively, I know this is being filmed as well, so I'm not actively going to go out to like a cloud API and attack it, just for the record here. I'm building my own model to attack, which is a random forest classifier. Very common, very tried and tested algorithm. And these are some probabilities that are being output from the model. So right here, it's pretty darn sure it's a 0.9, etc. You're generally getting some pretty high confidence predictions, right? I talked about high confidence predictions. If I introduce some anomalous input, you can see that the predictions are a little more wishy-washy. This is just one example too. It can get much more than that, but just for the purposes of demonstration, this is kind of the idea, right? And then I'm going to use a library called MBLearn here, one of these benchmarking tools, to actually step through how this works. And I put a reminder here for myself not to run this code, which is good because I'll forget. It takes a while to run it. That's why I don't want to run that yet. But essentially, this is just going to go ahead and do that data synthesis piece I was talking about. One model is going to try to work on each class to simplify the problem rather than having to pick all of them. It's just, you tell me binary, is this one a 1, a 2, etc. And something to look at is these are the features of that were input. And if you look, I don't know, it's a little hard to see, but you can see, like, for example, synth2 is in green. So that's a synthetic data representing category 2, and category 2 is in this X here. And the same goes for all the rest. So this data looks a lot like that data. And it's surprisingly easy to, the actual true data. And it's surprisingly easy to create data that appears just like the model's data. So let's go ahead and build our shadow models. We've got 5 shadow models we're putting to work here. And once again, we've got probabilities. So this is what the output of the shadow models look like. We've got the probabilities, the true class, and whether or not they think the record is in or out of the data set. And then finally, the attacker can suck in all these shadow models and can go through and query the target. And we've got some predictions here from the target. We've got our attack in data, which is basically the stuff that when I trained my target, right, I created my target, this is what's inside, this is what the private data set, and this is what's out. And the model's going to try to guess which is which. And a couple of metrics here. I mentioned metrics. Recall is kind of a metrics of false negatives, and that's something that in this type of attack you're really interested in. And precision is your false positives. We're getting a bit of a balanced attack here. This may not be that impressive, but it's beating a coin flip. And I didn't train for very long. I didn't iterate many times. And here we have identified some records and predicted whether they're in the data set or not. And I can't stress enough that if you were doing this, in the wild, you'd be submitting individual records to these models. All right, so let's jump over here, back again, to go into some of the security attack patterns. All right. So the first security attack pattern I wanted to get into was poisoning. It's probably the most easy to understand. This is typically thought of as a white box attack, but it doesn't have to be. And it's basically you inject bad examples during training. So this is basically you're training the model to do bad things, right? The model learns from the bad data, and the attacker knows how to manipulate the model. So it's fairly straightforward. What are some scenarios? Malicious user feedback, right? So feedback weaponization is another term you'll hear for this. So you can juice your statistics if you're a company. You can conduct reprisals. Reprisals are a really big deal this day and age, unfortunately, with our political landscapes. And then, of course, there's model compromise itself. So you want to simplify evasion. We'll look more at evasion later. That's usually after a model's been trained. But also, there might be financial gain in the model. If you invert a model that's predicting Bitcoin, and it's pretty good at predicting Bitcoin, then you might have gotten some intellectual property from that. And then once again, reprisals, embarrassment, I think you kind of get the picture. And this brings us to some defenses. Once again, you see rate limiting, obviously trying to stop people from constantly querying, but you got to keep in mind people are going to be adding emails, doing whatever tricks can be done. And these first three, which again, you have to do anyway if you want a decent model. You analyze the model drift when trained in the wild, snapshot, archive. So have kind of like a golden model, right? Like you look back to and say, okay, how different? We've been taking in data all the time. Our model is learning all the time. We love that, data scientists. We're learning, bringing in the data all the time. Oh, it's being weird, right? We can compare it to what's in the wild. And then the data itself. The models are really not what it's all about. It's really all about the data. It sounds cheesy, but really the quality of your data is what's driving this. And if you use poor data, unbalanced data, biased data, that's all going to play into it. Multi-stage testing I mentioned before, right? Like you're screening for health problems. This was kind of like directly appropriated from healthcare, and often involves putting human overrides in as well. So, it's interesting how as we get more digital, as we move into this automation age, analog systems and having a few switches in place can really help. I'm noticing that not just in what I'm talking about here, but just in general. And then finally, anomaly detection once again. All right, so we're nearly there. I wanted to just also talk about adversarial input and how we inject bad examples to trained models. So in this case, we didn't poison the model. We're simply just trying to trick it as it's been trained so that it fails in predictable ways and we can leverage failures for malicious use. And there's two types of attacks, targeted and untargeted. So once again, with our pelican here, if it's anything but a pelican after the attack, then we've succeeded. However, if we wanted it to be a flamingo, then that would be a targeted attack. So, and then some scenarios I'll run through. Bypassing malware and bypassing spam and phish filters are the ones that are kind of front and center right now. Again, I'm not going to name companies. I'm sure if you do some Googling, you're going to see some demonstrations, and some of the conferences recently, DEF CON, B-Sides, etc., they've detailed this. I am not going to be showing you live malware exploit codes in this demonstration, but that's obviously the concerns. And then deception, right? Inappropriate output and embarrassment, just making the model, we've seen this as well, where the models will do socially inappropriate things. And then the worst case, perhaps when we get into reinforcement learning, could be catastrophic failure of systems. The defenses are very similar. I'll call out CipherCat as a different benchmarking tool, as well as Clever Hans. Clever Hans, I don't know if anyone's ever heard the story of Clever Hans. He was a German horse. He was trained to solve arithmetic problems, but what he was really doing was looking for, and the trainer didn't realize this, thought he was teaching the horse to solve arithmetic, and what it was doing was looking at cues from the trainer, and when the trainer did something, made some kind of idiosyncratic body movement that they repeated, the horse learned from there. So, I don't know. I thought it was a clever name. Thought it was worth mentioning. All right, so our last demo here, and I'll probably talk through it because it'll take a little bit of time. I got 4 minutes. We're going to look at this adversarial input. And like I said, I'm not doing malware. I'm going to just do pictures of numbers. This is a classic data set called MNIST. It's maybe some of you working in the analytics space, I'm sure have heard of it. It's used for a lot of training and benchmarking. So we're using a small, very simple neural network here, and you can see with predictions here. So this is the output, and it kind of does a squasher over this here and determines, okay, 0, 1, 2, 3, 4, 5, 6, 7. Oh, weird. Oh, I'm sorry. Very sorry. Let me go back here to the PowerPoint. And show. Thank you, Mona. All right, let's go back. So again, this is a neural network, very simple one, one that you can find yourself that I'm just loading, and it's great for demonstrations to see kind of how this all works. So it's predicting a 7, and we're getting a 7. The network output, I'm just leaving that there to kind of see kind of a little bit under the hood. So that's the kind of the bit mask, right? That's giving us that 7. Or it's actually not really a bit mask. It's giving us essentially a probability. But a few more. So we predicted a 9. That's a pretty messy 9, but we got it. And a 3. So we did the 3. So you kind of get the picture here. And our accuracy is 87%. It's just a very simple metric in this case. We're just seeing, how many are we getting right? So let's take an untargeted attack for a spin here. And this doesn't always work, as you can see, that's kind of how it works in general, right? Again, with pen testing, but sometimes I like to see some that don't work. In this case, it did work because it's predicting a 2, and this is what I fed it. So that's great, right? Like, basically anything's a 2. Or in malware world, maybe anything's a clean URL or a clean signature. And a few more, and just a few more. One thing I'll just touch on, don't want to get too into the weeds here, but this is actually the step that does this. This is the gradient descent, where instead of walking down the hill, we're walking up the hill, trying to magnify the error. And as we get into a targeted attack, we're actually also just adding a few more terms. You see this x minus x target. So we're actually now saying, okay, give me a specific target. And let's see how we're doing. Again, we get a bit of randomization here. Did this one get it right? So nope, the network prediction was 8, and to a human, this is clearly a 2. This is why I would definitely advocate for, where possible, adding some human override into these systems. And just a few more. 9. Did it give me a 9? Nope, still thinks it's a 2. Really, really into 2s. 3's a 6. And did we get one right, at least, model? Nope. Okay, so sometimes it doesn't always work. So what do? One defense of this is to go ahead and just train the model itself, make the model focus on these kind of examples. And this is actually going to take a little bit of time for this pot to boil. Are we up? I'll tell you what, I will run through this, and we'll take a look at the end while I conclude. We'll let the pot boil. We're basically training the model on those examples, and we'll go back and look and see if we're now predicting correctly. So I just wanted to run through pretty quickly into some CVSS interpretations. So for membership inference, we're looking at, a network attack vector. I think we'd agree it's a pretty complex attack. Privileges required are low. I don't think none. You still need to authenticate. Again, CVSS experts may weigh in. No user interaction, and scope unchanged, confidentially high, and that's what we're ending up with. And then if we look at temporally, adding proof of concept code and workaround, that's where we end up. And then for functional code, we're bumping up a little higher. And for adversarial input in a white box scenario, obviously it's going to be lower because the high privilege is being required. And then a black box, we're going higher, again, mostly related to the privileges. And then finally, just to think about it, for a black box 0 day, with my experimentation, getting to about a 7.5. I will note that to get to that 7.5, it had to be an attack that would have would have compromised all three. So food for thought. And again, obviously, scope and privileges, there's things that can be done, and I welcome if there's CVSS experts and they want to talk a bit more about this, I'm happy to do that. I'm going to go again. I want to give credit where credit is due. I can't go through all of these now, but hopefully they're on the video. And these are all tremendous contributors to this field, as well as the GitHub repositories, where I was able to get the proof of concept exploit code and made some changes, but for demonstration purposes. And you can get all that here. And then I want to get to my key takeaways. So first of all, apps leveraging analytics are potentially vulnerable to privacy and security attacks. It's as simple as that. And machine learning vulnerabilities are heightened by this overfitting phenomena. You can mitigate with differential privacy, adversarial training, benchmarking, high-quality data, modeling best practices. All of this is good. This is still a research space. We haven't solved this problem. But you can't go wrong benchmarking and applying best practices. And I really urge you to reach out to your brothers and sisters in your analytics teams to do that. Expect to sacrifice some utility for safety, that balancing act, right? And then finally, incorporate data science expertise into your red and purple teams, and vice versa, and into your security monitoring. You've probably seen, if you're not familiar with this, that this is kind of some new concepts, a different way of kind of programming, and just take some time getting used to. So, you're going to need to do some penetration testing and some reconnaissance on this. And then finally, again, please spread the word. If nothing else, at least reach out to your leadership, to your teams, to your governments, your institutions, and talk about this. I'm reminded of there's a Greek myth, I don't know if anyone's heard of it, about Cassandra, who could predict anything, but she was powerless to stop it from happening. So I feel it's very, I don't know, it just resonates with me, and I'm hoping that that's not the scenario, because I do feel opinion combined with data that it's not here yet, but these types of exploits, attacks, vulnerabilities will soon be upon us. And I know I'm out of time, but let's just take a quick check and see if we made it to the finish line. Yeah, so we trained the model. The original prediction was for 2, and now we have 3. So our robust data set is helping us there. Same thing, original 0, 5, and that's clearly a 5. So I apologize for going over. Thank you first. Thank you, everyone, for bearing with me. I know it's a lot of complexity, but hopefully I've conveyed some new information. And if you have any questions now, or if we're out of time later, I'm here. I'm here for you. This is why I came to Oslo. And once again, thank you, everyone.
Thank you,
So
Dave.
those of you who want to ask questions will have to sacrifice going to the loo.
But yeah, thank you for introducing us to your family, and thank you for coming here.
No problem.
Thanks.
Thank you.
Okay, awesome. Thank you.